I think at most there'll be 20 people, so there's no problem in using a classroom. I think it will work better.
Very good. So I think we can get started with the last lecture of the last mini course.
Thanks a lot.
Diane?
Yeah, I'm happy to be talking on the last day of the Bootstrap meeting. Okay, so I'm not connected. Yes.
Translate it up by a little.
Yes.
Perfect.
Thank you. Okay, so last time we discussed a little bit about the BFSS Bootstrap. So now I'm just going to show you some results. So that's basically where we ended. I'm going to show you some results for BFSS Bootstrap and related models. And then we're going to turn to a new subject, which is the time-dependent Bootstrap. Okay, so to show you the results, I thought I would just show you some figures so we don't have to sketch and you can see how precise the results are. So here is not BFSS. This is the D equals 9 model. So this is for the model, the purely bosonic matrix model. So this is for this model where I runs from 1 all the way up to D. Okay, so this is for the D equals 9 model, and it's a little bit like BFSS, except there's no fermions, of course. Okay, so what you see is that in orange we have some analytic curves. Those were the analytic curves that I derived for you on the first lecture, right? So those were the simple analytic curves that you can derive by hand, and that already gives you some peninsula. Okay, and as I said, well, you are optimistic, since there's a kink, that the exact solution is somewhere near the kink, right? So this graph starts at 0.25, notice on the x-axis. And you can see that at d equals 9, we can compare to large D and Monte Carlo, and they're pretty close to the tip of the peninsula. But if we just go further in the Bootstrap, we eventually find an island. So what's a little bit interesting is if we start with the analytic result, that was a level 5 result, okay? When we go up to level 6, level 7, level 8, nothing actually changes. The bounds do not improve until we go to level 10. So at level 10, suddenly we get an island. So that's this gray region here. And then as we go to higher levels, so this is a level 11, we get a very tiny island. So the red dot in this picture is now this tiny little island, and you see we get several digits of precision. Okay, so that was for d equals 9. We can also do d equals 2. We get something kind of similar. There it's a little bit different just because we can't do a large D expansion reliably, right? So again, we have a very similar shape. We have some analytic bounds that we got to level 5. We have to wait until level 10 to see an island. And then we get the smaller red island. And we went even higher, to even higher levels in this case, up to level 14. So we got some very tiny little blue island, which is not visible at all in the original picture. And we can compare to some Monte Carlo results. So the green dashed curve is the Monte Carlo result. They didn't compute trace x squared, so unfortunately it's just a line. And there's also some interesting work by other authors which use some kind of truncation method of the loop equations. And that's indicated by this purple dot. And you see it's pretty close to the exact result, but not quite. Okay, very good. We can also consider a variant of this model where we add a mass term, so just the m squared x squared term. And then the behavior of the Bootstrap is very different. So unlike the previous case where we had to go up to level 10 to get an island, here we get an island at much lower levels. So that's a little bit expected. The idea is that somehow these classically flat directions, so these models don't have flat directions quantum mechanically, but just classically there's some direction where the potential looks flat, right? And somehow our intuition is that these flat directions are more challenging for the Bootstrap. So if you add some mass squared term, the Bootstrap does very good even at low levels. So again, we go up to pretty high level, we get an extremely tiny island. I should say that there's also Monte Carlo results for the d equals 2 model that we compared to, but actually our first island already excludes that result. I'm also showing a plot now from these other authors who also studied the massive model for d equals 2. So they studied this model with the trace x squared potential for d equals 2. And then they studied the thermal physics of this model. So the previous plots were all at 0 energy, okay, or sorry, at minimal energy. So we could also study the model at finite energy, and then I have to tell you whether it's gauged or ungauged, and they chose to study the ungauged case. So here they plot energy as a function of temperature, and for any temperature there's an island, right? There's upper and lower bounds for the energy, okay? So I think this gives us hope. Presumably, if we use our high precision results combined with their methods of implementing this energy inequality, we could get to a very tiny island for the energy, and therefore map out the thermodynamics to high precision. Okay, so now let's go to BFSS. Okay, so the green curve, so the gray and green curves are analytic curves that you can derive using very similar ideas to what I already presented. So we did, as an exercise, deriving the peninsula at low levels, right, for the purely bosonic models. And a very slight variant of that calculation, now just involving some fermions, gives you this green peninsula, okay? And again, there's a sharp kink, and you would think that the exact result should be somewhere close to the kink. And so we can compare to the Monte Carlo result, which I drew in this cross, okay? So the cross is pretty close to the kink, and as we go up in level, we see that the peninsula recedes and it approaches somewhat the Monte Carlo result, okay? Now notice we only went up to level 9. So in the previous plots I told you that for the massless case, level 10 is where you get an island. And between level 5 and level 10, basically nothing happens in the bosonic case, in the purely bosonic case. This is a kind of curious feature of the bootstrap that we don't fully understand. So in the supersymmetric case, there is an improvement, but it's kind of a minor improvement, right? So the difference between the tip of the peninsula in green and the tip of the peninsula in black is definitely significant. Like it goes from roughly 0.2 to like 0.3 perhaps. But qualitatively, the shape of the peninsula doesn't look that much different at level 9 versus level 4. So we're hoping that at level at level 10, the shape of this constraint dramatically changes in accordance with our bosonic plots. Okay, but as of now, that's speculation, but hopefully we will get an island at higher levels. I should also say that the level 9 results are still using extremely modest computational resources, okay? So you can produce this level 9, this is our best peninsula for BFSS. You can produce it on a laptop with very limited computation, like I think 1 hour, 2 hours of computation to make this curve. Okay. So we certainly haven't gotten to the point where we're running out of computational resources. So there should be no, in principle, reason why we can't go to significantly higher level, like level 11, level 12. Okay, so this was a plot of the kinetic energy as a function of trace x squared. So just to clarify something, in the previous, so when I was comparing to the bosonic plots, I was plotting the ground state energy as a, so I was plotting E versus trace x squared, right? Of course, E for a supersymmetric, in the supersymmetric model is just 0. But if you like, in the previous plots, E could also be related to the kinetic energy by the Viral theorem, right? So in the previous cases, you could also think of the y-axis as the kinetic energy, and so the analogy is very close in terms of the bosonic and the supersymmetric models. Okay, we can also plot other observables. So here's now a 3-dimensional plot, and on the z-axis, I'm plotting trace OO, which is this quantity that we talked about yesterday. So this is the quantity psi alpha, psi beta, psi eta, psi epsilon, and then we contract with just delta alpha beta and delta eta epsilon. So we call this trace OO. You could also plot trace OI, which would be where you have, instead of delta functions, you would have the gamma matrices. Those are some very simple observables. So these are, this observable is level 6, and the other two, the energy is level 4, the trace x squared is level 2. These are some like basis of simple operators that we could plot. And we see the peninsula, it also sort of extends into the z direction. Okay. The maximum height of this boot actually asymptote. So this boot actually asymptotes. So it has a maximum height. Okay, it doesn't keep growing forever. All right, here's another observable. This is now a level 4 observable. Trace x squared, x squared. So that means trace xi, xi. So this means trace xi, xi, xj, xj. Okay. With some normalization. Okay. And we plot that as a function of trace x squared. Okay, so once again, we have some low-level bounds. You see at very low level, there's simply no lower bound on trace x squared at all, right? You have to go at least up to level 5 to get a lower bound on trace x squared. That's where the peninsula appeared, right? And then as we go to higher and higher levels, the bound on trace x squared recedes. But something slightly interesting is that it starts out straight vertical, but once you get to level level 7, I guess. Yeah, sorry, level 7, the line is not quite vertical. There's a slope here, a very large slope. Okay, so we think that that means that the true value of trace x squared is not quite the lower bound, right? But probably closer to the tip of this peninsula. So slightly to the right of the peninsula that we drew in the previous plots. Okay, something slightly interesting is that this gray curve was actually derived essentially in older work. So Polchinski in 1999 basically derived this gray curve that I've drawn, okay? And you see that it gives a lower bound on trace x to the 4th, roughly, but no lower bound on trace x squared. So why did he do this? Well, it turns out there was actually a controversy about the size of the bound state wave function in BFSS. So actually, in the original BFSS paper, there were two different estimates given for the size of the bound state wave function. The n scalings were actually different. One is just based on the sort of Tooth scaling, which is the correct answer. Another one is kind of more thinking about the M-theory region. So they thought that the bound state wave function was much smaller based on a different line of reasoning. And they were both sort of non-rigorous arguments. Polchinski, using what we now appreciate as bootstrap ideas, derived by hand this gray curve, which showed that trace x to the 4th has to be at least this number, right? So if it has to be at least this number, it rules out the possibility that it's extremely tiny. So the other estimate would be essentially 0 in the Tooth limit, okay? So he proved that trace x to the 4th has to be order 1 in Tooth units, okay? Now, of course, we can improve the bound a lot. First of all, by including fermions, we have a lower bound on trace x squared, whereas previously there was no lower bound. And of course, the bound for trace x to the 4th is also improving. Of course, the dream would be if there's an island at higher levels, and we could get a very precise estimate. Even if there were no islands, if we went to very high levels and you saw the peninsula really converging, I think that would be, reasonable evidence that we've actually isolated the theory. Okay, so just some caveats now that I've mentioned already. So when I was comparing to Monte Carlo, I wanted to show you just some of their plots without my interpretation of their results, or giving you their interpretation instead of my interpretation. So here is one of their key figures. This is the energy as a function of temperature. And you see that they can go to temperatures that are about 0.25 in Tooth units, right? So recall that the supergravity regime is the very low energy regime. So we're testing, also in our bootstrap method so far, we've been working at exactly 0 energy, right? We've imposed supersymmetry and so forth. They can't quite go to 0 temperatures because you have to make a very big Euclidean time circle, right? So they can go to about 0.25, and they see sort of reasonable agreement with the supergravity. So supergravity prediction is just this curve, this dark, I guess, blue curve. Can't quite tell what color it is. But this dark blue curve kind of agrees with their first result. But I think it's fair to say that they don't really see the supergravity scaling, which would involve going to temperatures much lower than 0.25 in this plot. What they do is they say, well, you can fit this alpha prime cube correction that we discussed. And if you fit this alpha prime cube correction, then they get a very nice fit, right? So this is the orange plot that they show. Okay, another caveat. So here is, so when we did the comparison to Monte Carlo, as I mentioned, they have to do some kind of regularization, which means in this context that they went to the BMN model instead of the BFSS model. And then they tried to remove the BMN mass. So mu here is the BMN mass term. And to compare with BFSS, you should really take n goes to infinity, and then mu goes to 0, right? So what they do is they work at finite n, of course, and then they try to take mu small. But you see that there's something a little bit funny. So this blue curve is the trace x squared observable that we've been discussing. And you see that a trace x squared has some kind of non-monotonic behavior according to their plot. So they really want to calculate trace x squared at 0 mu. But they notice that as you take mu small, trace x squared actually seems to be getting very big. Okay? And that's related to the flat directions. So they say that, well, they say it right here that it's associated with the flat directions in the BFSS limit. So what they end up doing is they take mu at relatively large values and then try to extrapolate backwards. So this is just to say that the metastability is a real issue. Yeah.
How far is the M-theory regime from what's shown in these plots?
The M-theory regime. So I guess, yeah. Well, first I guess you have to go beyond the Tuft regime, and they are still sort of in the Tuft parameter of order 1, right? So
well, in this, I guess there's not enough info to tell from this plot because you didn't say what value of n is. So.
Yeah, I think this is up to n equals 32. And what they did is, yeah, they tried to, I mean, they work with Tuft scaling so that these plots, I think some of the points might be n equals 16 and some are n equals 32. And they work with the Tuft scaling so that they're at temperatures of order 1. I think they also checked that large n factorization is working pretty well. So that also suggests that they're in the Tuft regime. But it is true that they also tried to fit some 1 over n squared corrections. So they attempt to obtain this first 1 over n squared correction that's related to the M theory R to the 4 term that we discussed.
So I was actually more kind of interested in whether it's possible to see the phase transition to the, you know, this caged black hole.
Yeah, I believe there was some work by Masanori on that question, but I'm not too familiar with it anymore. Yeah, so just in case it wasn't clear from yesterday, those phase transitions all occur at t equals 0 in Tuft units, right? So they're temperature to some inverse power of n. Okay, so those were the BFSS results. I'm happy to take any questions on that. If not, we can start the time-dependent bootstrap, and I think we don't need the slides now.
You done? Are you planning to do BMN?
I do not plan on doing BMN. I do think that there's, I've heard of some ongoing work. I'm not exactly sure what the status of it is, trying to do BMN by other authors. And one interesting thing is that, well, in BMN, there's some localization calculation you can do for trace C's to the sum powers. And you could input that as a, you know, constraint into the bootstrap directly. So.
But by the way, do you know what is the actual scaling exponent of the caged black hole in the low temperature regime?
The scaling exponent of the what black hole?
Yeah, the black hole is localized on the M3 circle.
You mean the temperature scaling?
Yeah.
The energy as a.
Like how does it differ from this t to the 9/5?
It's definitely a different exponent. I don't remember the exponent. Yeah. It's some other rational exponent. Yeah, I guess we could estimate it easily from the Schwarzschild solution. Yeah, yeah. Okay, so let's discuss now the time-dependent bootstrap. So part of the motivation for the time-dependent bootstrap was sort of this discussion that we were having yesterday about the two-point functions, right? So the two-point functions are some very clear prediction from holography, whereas the one-point functions are a bit murky from the holographic point of view. I think there are probably other applications of the one-point functions, for example, to scattering. But from the holographic point of view, the clearest predictions are about correlation functions. And you need to have some time separation in order to really go into the regime where you can trust supergravity, right? So that's just one motivation. Of course, in general, we care about time-dependent correlators. So let me now discuss that. So the simplest kind of time-dependent setup that I'm going to discuss is just the ground state two-point function. So the Euclidean ground state two-point function. We will also discuss the thermal two-point function. Okay. So we can keep the discussion fairly general now. So I'm imagining some simple quantum system. We want to compute the Euclidean two-point function. And again, we can define some matrix, Mij, right, where we have some operators Oi, Oj, right? And this matrix, by reflection positivity, is positive semi-definite for all tau, right? So in Euclidean signature, we're computing some operator O and some other operator O bar, right? And we can cut to the Euclidean path integral and think of this as a bra and a ket, and so this inner product matrix has to be positive semi-definite, right? So that's one kind of constraint that we would like to impose. What are the other kind of constraints? Well, they're all extremely elementary. First of all, we would like to impose the Heisenberg equations of motion, right? So that means we would like to impose that partial tau of m is equal to something. So what is something? Well, let's define the commutator of H with OI to be some matrix, okay? So D, well, I'm going to define it like this. Oh, sorry, OJ. Okay, then we can write this as MD, right? So this is just the Heisenberg equations of motion. I'm imagining that we have some simple basis of operators, like in the previous discussion. So we arrange OIs to be like products of X's and P's, for example. And then we can very explicitly compute what this matrix is, right? So we just use the commutation relations of the Hamiltonian, and we know explicitly what this D matrix is, okay? Of course, we can write down this equation, but it doesn't mean we can solve it. If we could solve it, then we could solve the quantum system. We won't need to do any bootstrap. So we're imagining that we can compute D easily, but we can't easily solve the Heisenberg equations of motion. Okay? So this is one constraint. Another constraint is just time and translation invariance, right? So that says that if we, for example, if we time differentiate this matrix, we can either think of the Hamiltonian as acting on this operator, or we can think of it as acting on this operator, because by time translation invariance, we can think of this as 0 and minus tau, right? So we could think of the Hamiltonian as acting either way, and that tells us that MD is equal to D dagger M. Okay, this is just time translation invariance. Third ingredient, perhaps you can guess. So in the ground state, I've been going on and on about this ground state positivity condition. So we're going to impose that as well. So we're going to define a matrix N of tau. It's just going to be equal to this matrix that we've written down before. The only difference now is that it's time dependent, right? And this matrix cal n is positive semi-definite, right? Now, as you see from the definition here, this matrix n is simply related to md. It's basically, sorry, minus md. It's basically the time derivative of m, right? Okay, so these are the constraints that we want to impose. In addition, if we have some global symmetries, well, that would tell us that this cal m matrix commutes with some other matrix R, which implements the global symmetry, but that's a detail. Okay, so the problem that we would like to solve using Bootstrap is the following. So this is the primal problem. Well, it's basically what I already wrote. We want to minimize something, right? Let's say we're interested in some objective function that looks like this. So O hat here just picks...
Sorry, the very last step was a bit too fast. Why is n positive?
N is positive because we think of this, okay, using time translation invariance, we think of this matrix as basically a bra and a ket where we've inserted the Hamiltonian, right? So that's some excited state energy. And then it's the other term just acts, the H just acts on here, and that's just the ground state energy. So it's just a difference of two energies. One is the energy of the excited state, which is obtained by having O in the bra and the ket. And the other one is just basically the ground state energy. So this just says that a perturbation to the ground state increases the energy. This is the matrix version. So I was just explaining the diagonals, but simple generalization of that argument.
Okay. So 0.3 works for the ground state. The
For
other
just the ground
ones
state.
work for everything.
Yes, the other two are, yeah, perfect for thermal state, for example. Yeah. Okay, so the idea is that we want to calculate something. So for example, we might want to calculate x of t, x of 0, right, in the ground state. So t here is some fixed Euclidean time, okay? And we encode that by putting it into this form, right? So this is capital T. We, we choose some O which just projects onto the component of M that we care about. So if M is some giant matrix, right, it has many different correlators. If we care about one particular correlator, we use this O hat to encode which correlator we care about. And we would like to, let's say, minimize, define the lower bound on that correlator. Of course, if we put a minus sign, it would become a maximized problem. So we would like to derive some lower and upper bounds on this quantity, subject to those constraints. Okay, so I'm not going to rewrite them again, but we want these three things to be satisfied. Okay, so how are we going to use Bootstrap to solve this problem? Well, as I said, the very tricky thing is this equation, right? If we could solve this equation, then we can basically solve the quantum system. So it doesn't seem like we've done anything so far to simplify the problem. Okay. But, so subject to 1 through 3. But sort of as pro bootstrappers, we know one strategy. So one strategy is to derive the dual problem. So let's try to derive the dual problem and see if there's any advantages of the dual problem compared to the primal problem, okay? And we will see that there is an advantage. Okay. So let's derive the dual problem associated to this time-dependent problem. Okay, so what do we do? Well, we write down an action, right? We write down an action. The action is this thing, trace O hat M. This is the thing that we want to extremize. And then we have some Lagrange multipliers, right? So these are all time-dependent Lagrange multipliers now, right? So what are the Lagrange multipliers? We're going to have 3 of them. Okay, so I'm going to call the one associated with this, I'm going to call it lambda d. The notation is kind of for historical reasons. This one I'm going to call lambda a, and this one I'm going to call lambda g. Okay, they're just 3 Lagrange multipliers that implement these constraints. Okay, so let's write down the Lagrange multipliers. Okay, so we have d tau minus md. Now, I'm going to do something that seems a little silly. So I'm going to write 1/2 md plus d dagger m. Using this equation, I'm allowed to do that, right? And I'm going to introduce the Lagrange multiplier, lambda, what did I call it? Lambda a, lambda d, right? That implements this constraint. So let's just think about exactly what I'm talking about, right? So MD are matrices, right? So it has some matrix index ij. These are not the SUN matrices, right? These are just the matrices of the giant matrix bootstrap, the giant inner product positivity. So those are the matrix indices. This thing, lambda d, is a Lagrange multiplier. It also has matrix indices, right? So it has the same matrix indices that this guy has. Okay. So that's one Lagrange multiplier. Okay. Now I'm going to add, okay, these other constraints, right? So we have md minus d dagger m. And we have one more constraint, which is trace lambda g times this thing, right? So we have n plus md. Again, I'm going to use the same trick to write this as 1/2 md plus d dagger m.
I think you have an m missing, right, in the first constraint? D tau of m, right?
Ah, sorry, d tau m.
In the lambda d, d tau of m.
D tau, thank you. Thanks a lot. Now, so far I've implemented these things. I haven't implemented positivity, right? So positivity is implemented by yet 2 more Lagrange multipliers, right? We have a capital lambda m, and we have a capital lambda n times n. So these things are all functions of time, right? They're in the integral. We're optimizing something that is time independent, like capital tau, capital T here. Okay, so let's just work this out. So what are we going to do? Well, we're going to collect all terms that involve m and n, and we're going to integrate by parts. Okay, so let's do the integration by parts. So we remove the d tau. Well, there'll be a lambda d here, and a lambda d. We move the d tau here. That changes the sign, right? And then we also get some boundary terms, right? So what are the boundary terms? So we'd have some boundary term, which is just lambda d evaluated at time t times m evaluated time t, and another term, which would be trace lambda d at 0, m of 0. Okay, then we collect all the m terms, and we impose the equations of motion for m. Okay, so let me just write it to be a little bit more clear. So sorry. What am I doing? So we have that term. We have minus 1/2. Now I'm going to use cyclicity of the trace to move the d to this side, right? So there's a lambda here. There's a lambda here. And I'm moving the d through, using the cyclicity of the trace, to the left-hand side of that term, right? So this whole thing is going to be multiplied by m, right? That's what we're doing. And then we have plus 1/2 lambda d dagger. And we have a similar kind of term. This kind of thing will give us a similar term here, right? So we have a d lambda g plus 1/2 lambda g d dagger, right? And then we have the lambda a term, which basically does not change. So the only thing we do is, again, we move the d to the other side. So and we have lambda a d dagger, right? And finally, we collect the capital lambda m, which enforce the positivity of m. Right? So capital lambda of m is defined to be positive semi-definite in the dual problem. Okay, and we have a similar term for lambda n. Okay, so lambda n is a little bit less painful. So we again have this trace. Again, basically the same kind of trick. We would have some d lambda g. We only have lambda g here and lambda n, actually. The lambda g we already took care of right here, the term with the g's. So we just have this term and a lambda n. Okay. This whole thing is multiplying n. Okay. Okay. So now we can vary with respect to m and n very easily, and we derive the dual problem. Yes, thank you. Yeah, lambda n is also symmetric and positive. Sorry, lambda n is also symmetric and positive. Okay, so let's derive the dual problem. Well, it's basically, you can read it off from here, right? So first of all, we can just solve for lambda m. So lambda m is just equal to this thing here, right? So lambda m is equal to this term here, which perhaps I won't rewrite. Well, the interesting thing is that we get some, okay, let me write it actually. Let's collect the, and then we also have d lambda a minus lambda a d dagger. So this whole thing is positive semi-definite, right? So lambda n could be anything. Lambda m, sorry, could be anything. So this equation tells us nothing except for the fact that it's positive semi-definite. So we can just forget about lambda m and enforce that this quantity is positive semi-definite, right? varying with respect to n also gives us now a very simple condition, which is basically the same. So we just derived that lambda g is positive semi-definite, right? Following the exact same logic. Now, that's almost right. We also have to vary with respect to the boundary value. So we have the boundary value m of t, which is an unknown, right? We don't know what m of t is. That's the thing that we wanted to calculate. So varying with respect to that, we look at the terms that we got by integration from parts, right? So integration by parts gave us this extra term, and varying with respect to capital M of t just sets O hat equals to lambda d t, right? And finally, we have one more term that's left over, right? So in this action, right, the variation with respect to m and m enforces these equations. Plugging it back into the action, we get 0. The only term that survives is one other term that we got from integration by parts, which was this thing. Right? So at the end of the day, we started with a problem where we minimize over this thing. We end up with a problem where we maximize over trace lambda d m0. So this is just the time-independent object, right? But it's subject to these conditions, right? So in particular, it's the objective function that we're interested in gets encoded in the boundary value of lambda d of t. Right? Now, what is the point of doing this? Well, we derived the dual problem, but the interesting thing is now that we no longer have to solve the Heisenberg equation of motion. So that's like the most key point, okay? The Heisenberg equation of motion somehow got translated into a matrix inequality in this formalism, right? So in other words, okay, these are some time-dependent functions, right? So the first line and the second line, these are time-dependent functions. So this holds for tau between 0 and capital T. So now we no longer have to solve any equations besides this equation, of course. But this is just some boundary condition, basically. These two equations are now inequalities that hold for all time tau. So the idea is you just try to guess some Lagrange multiplier. Of course, you don't actually just guess, you use STP. But conceptually, imagine that you just have some lambda d's and lambda a's and lambda g's. You guess some test function, right? If you can show that this test function satisfies this inequality, satisfies these two inequalities, then you can use that as a valid, as a trial solution, basically, that solves the constraints of the dual problem and immediately get bound on this action, right? This action was nothing but the same action that we started with in the primal problem, which was this thing. Okay? So the idea is you just guess some arbitrary test functions that satisfy these constraints, and you can derive a rigorous bound on trace O hat m. Okay? Is the strategy kind of clear? Okay, so of course, this is still an infinite dimensional problem now because we have these functions of tau. But we can deal with this in...
Can I just ask a trivial question, just to clarify? So O hat is a matrix with the ones and zeros to extract, for example, XX from M.
Indeed,
right?
yes. And yeah, just to emphasize again, lambda d is some matrix. So both of these are matrices. Okay, so we still have an infinite dimensional problem in a certain sense because it's a function of tau. But we can deal with this in two different ways. So one way is the non-rigorous way, and this was first proposed in this paper in a slightly different context by these authors. Okay. So the method is you basically choose any spline function or whatever you want for these lambdas, and you just make a grid of taus, tau between 0 and capital T, and you test positivity on that grid. That's roughly what they did. To say it slightly better, you can make a barrier function that's a sum of a bunch of points between 0 and t, and that barrier function tries to enforce this positivity constraint. That's slightly non-rigorous, of course, because you could worry that in one of the fine grids that you didn't test, the function actually goes negative, and therefore your trial function is not actually a valid solution of the constraints. Okay, but that's kind of a minor worry because if in practice you're dealing with some finite spline function. So it's a function with a finite number of parameters, and you can check on a very fine grid, on a grid size that is much, let's say, larger than the number of parameters, and then it would be sort of a conspiracy that you really violate this kind of bound. Okay? So that's one method, the sort of non-rigorous method of just checking on a grid. another method which is completely rigorous is the following. So I'm only going to sketch for you this method, but I think it'll be sufficient to get the idea. So the idea is just to write these lambdas, right? So lambda, we have various lambdas. Let's just call it lambda vector, right? Lambda vector we write in as lambda I times phi I as a function of tau. So these are just coefficients now. So these are just coefficients. These are matrix valued coefficients though, but they're time independent. And these are scalars. These are scalars that are now functions of time, right? And the idea is that we choose these functions of time to be completely positive. So they're scalars. For each I, this phi I of tau is positive. Okay, so this gives us some ansatz for all the lambdas. And then we just plug it into this equation. Okay, we plug it into this equation, and the idea is well, when you plug into this equation, there will be something which is proportional to phi I, right? So for example, we'll have phi I out here, and we'll have a bunch of labels now here, right? So this is something that's a matrix with no time dependence times something which is time dependent. And since these are all positive, the idea is that if this is positive semi-definite, then for sure this will be satisfied for all times tau. Okay? So we converted it into just a time-independent problem with some more indices. Yes? Yeah, that's an ansatz. So we're allowed to take as a trial function anything we want. I'm saying suppose that we take as a trial function something where it's equal to lambda I times a positive function. So there's no requirement that this thing here has to be positive. There's only a requirement that this scalar function is a positive function. Does that, perhaps I didn't understand the question. Lambda i's are just matrices. Okay, they're either symmetric or anti-symmetric matrices. Yeah, so yeah, lambda i's are either Hermitian or anti-Hermitian matrices. Phi i's are chosen to be positive functions for all time taus. And then the point is...
Can I ask
yes.
one question? Is there did we make an assumption that D is a matrix of numbers?
Yes.
Okay. Is that a huge assumption, or it's okay?
It's okay. So very concretely, you should think of this as like OIs could be something like, you know, XP, whatever, right? And it's a complete basis for the operators, right? So maybe O1 is just X. Okay. O2 could be P. O3 could be, I don't know, X squared, etc. Right?
And is there some issue at the boundaries in that?
Yes, there is some issue. There is some issue at the boundaries, which I'm glossing over. In order to make this problem finite, so we want to work with some finite matrix D, we need to actually relax this formalism slightly. So yeah, I'm happy to discuss this a little bit offline. Yeah. The point is that you just take any equations which would take M outside of the finite range, and you just delete those constraints. That's the basic idea. So it's a completely rigorous thing. So you just impose something slightly weaker than this equation.
Sorry.
Yes.
You also have a derivative term acting on phi?
Yes, very good. Excellent. Excellent question. Yeah. So yes, we assume that we can rewrite d tau phi I as some other, okay, there's another d here, calligraphic d, ij phi j. So we assume that whatever basis of positive functions that we have, we can write the derivative acting on one of the phi's in terms of the others. Yeah, so you should have in mind that phi's are like some spline functions, right? There's some like, you know, polynomials in little windows which are continuous in some way. And if you differentiate some polynomial, you still get a polynomial, so it's okay. That's a little bit fast, but that's basically the idea.
Take monotonic functions is not enough to...
No, you cannot take monotonic functions, that's correct. You need some wiggly functions. Yeah. Yes?
So what you're saying that you're imposing these positivity conditions for all i's. So this is obviously a sufficient condition, but it's not maybe necessary.
True.
So that's one question.
Yes.
is there some sort of statement that if you try it hard enough, then that's actually you're not going to lose anything? And second question is, can you just use polynomials and use the usual, the same as we use in numerical bootstrap for
Yes,
CFTs?
yes. Thanks for the question. So the first question is, yeah, certainly this is a valid ansatz, but am I sure that it's going to converge? And the answer is no, I'm not sure that it's going to converge. But in practice, I'll show you some evidence that it actually does. But of course, yeah, so we're not really worried about convergence as long as we get some rigorous bounds that we can trust. So that's one comment. Okay. Second question is, can we use something like STPB? And the answer is yes. So it's slightly subtle, and I'm happy to discuss it offline. So we can make some polynomial ansatz for these guys. Turns out, well, yeah, it turns out you need a rational ansatz and not a polynomial ansatz, just because of the way the boundary conditions are enforced. So something I glossed over was this constraint, and this constraint needs to be enforced in some way. So turns out that requires using some rational functions, but we believe that it could also be used. We believe that STPB could also be used to solve this problem. Yeah, thanks for the questions. Okay, great. So, yeah.
Yeah, regarding the question whether this is not only just as necessary but also sufficient, I think it depends on the situation. For the polynomial, it is proved, but for more general situation, I'm not aware of very generic proof that what is the exact criteria for it to be necessary and sufficient. Yeah.
Yeah. Thanks. Yeah. Yeah. Okay. Let me show you now two things. So one is an analytic bound, and the other will be some numerics. Okay. So the analytic bound is extremely simple, but it will actually partially address this question that you're asking. Okay. So for the analytic bound, we can actually forget about the dual problem and just work directly for the primal problem. Okay. The bound is sort of morally similar to the other analytic bounds that I've derived in the sense that it's extremely elementary. And in fact, secretly was the same as one of the analytic bounds that I showed you earlier. Okay, so the idea is, let's consider a generic situation where we have a Hamiltonian of one or more non-relativistic particles with an arbitrary potential. Okay, I'm going to have in mind just one particle with some potential, but this proof goes through almost completely for the one-matrix quantum mechanics. Okay, and it also goes through actually for higher matrix quantum mechanics with some very minor modifications. Okay, so. If you like, you can think of X as either a matrix or just as an ordinary position of a quantum particle. Okay, so the idea is we consider the following matrix. So M here is going to have this structure, X tau, X0, X tau, P0, P0, X tau, and P tau, P0. Okay, so it's just a 2x2 positivity matrix where we chose O1 to be X and O2 to be P. Right? And this matrix is positive semi-definite for all tau. Right? Now, let's call this, so these are the ground state correlators. Let's call them G. So G of tau is the first entry. And then we basically have I G prime tau here and minus I G prime tau here. And this gives us G double prime of tau. Okay, that follows just from using the Hamiltonian commutation relations. It's basically just that P is the canonical conjugate of X, right? But it's using the same ingredients as what I explained on that left board. Okay, so this matrix is positive semi-definite. What can we learn? So first, we learn that G of tau itself is positive. That's no surprise. Now we also learn that the determinant of this matrix is positive. So that's G double prime plus G prime squared. That quantity is positive. Right? Hopefully I got the signs right. This quantity, well, because G is positive, we can divide it by G squared. This is also a true statement. Right? And then we identify this. So we identify this with log of G double prime. Right? F prime G minus F G prime. Okay, so this is log G prime squared. Log G double prime, sorry. This quantity has to be greater than or equal to 0. So we can derive a bound, right? The bound would be when it's equal to 0. When it's equal to 0, we now know that log g at most is a linear function, right? So what we've derived is that log g is at most m tau plus log g of 0. Right? So we can rewrite this as g is bigger than or equal to g0 e to the minus m tau. By convention, I put a minus sign here. Right? And in fact, we can say what m is, right? So we can take g prime at 0. G prime at 0 is just the expectation value of xp, basically, right? And that gives you some factor of 1/2. Okay? So g prime of 0 is basically 1/2. That's also, on the other hand, equal to minus m g0. So this thing is equal to 1/2. I think I got a sign wrong. It should be minus 1/2. So we learned that m is just equal to 1/2 g0. So what does this say? It says if you know the initial value of g, which was just the expectation value of x squared, right? If you know x squared in the ground state, you immediately get a time-dependent bound. Okay? So this is some trivial bound, and it's exponentially decaying. This exponent you could interpret as a bound on the first excited state of the system. And actually, you saw this bound before. So previously I said, like in these matrix models, you have a bound on the adjoint, which is given by 1/2 trace x squared. That's basically the same idea as what we've done here. Okay, but it's some time-dependent bound, and this is actually the level 4 bound, like so-called level 4 bound analytically that we expect from doing this bootstrap problem. Okay, so now we can make some plots. So that was the analytic bound. It's not super interesting, but it is true, and it's true regardless of the potential, and as I said, it generalizes almost immediately to matrix quantum mechanics. Now, we can make some plots. Now using this whole spline business and going to the dual problem. And one thing we can do, for example, is just look at level 4. So at level 4, we can plot, let's say, x tau, x0. Here I could be talking about either just the anharmonic oscillator, for example, or I could be talking about matrix quantum mechanics. The plots are almost identical. We input some initial value of x squared in the ground state. We go through this whole rigmarole, and we derive some bound, right? So we get some bound like this. It decays, and we can compare that to the analytic bound at level 4. And the point is that it's not exactly the same. It's not exactly the same because the spline parameters are finite. We have a finite basis of splines. As we increase the basis, we get very, very close to the exact level 4 bound. Okay? But of course, this was just the level 4 bound. It's not that exciting. It's just some particular shape. But this gives us some confidence that our spline basis is working, you know, that we're converging to something which is close to the optimal level 4 bound. Then we go up to higher levels. So we could do level 6. Then we'll get a slightly better bound numerically, right? So now the rest of the curves, we don't know how to derive them analytically, but we get some numerical bounds. So actually, maybe if you can bring back the slides. Sorry.
Maybe I can ask just one quick question before that. So I'm still a bit confused by these D being numbers and the statement that you said that's obvious, because I agree that it would be obvious if D was a matrix whose size was n squared by n squared, not n by n, where n is the size of m. So in general, the fact that you can write derivative of m as m times d seems very non-trivial. For example, in your example, you had x and p as the rows, right?
Yes.
If you had x and p square, it will not be true anymore, right? Then you would have g prime prime, and it will not be true that...
Yes. So the strategy that we do is...
It's a big assumption on the space, on the choice of m.
Yeah, let me say a little bit more concretely. So we organize by level. So the level is defined so that the commutator with the Hamiltonian increases the level by 1. So this matrix D is just a matrix that increases the level of the operators by 1. So we organize it in that way. And so what you said is true. That's because we're putting a level 4 operator in this thing. When you organize it in this way, the D matrix will only move you down 1 level. Now, it's true that at the end, so M is some big matrix. At the end of the matrices, you will have some equations that bring you out of this subspace.
Okay, no, I got it.
Yeah,
Okay.
you got it.
It's that row,
Yeah.
row by row, they only talk to neighboring rows.
Yes,
okay, that's
yes.
okay. So you want slides, right?
Yes, if we could get the, if not, it's not crucial.
Yeah,
but-
could we get the slides, Tiago?
Yeah, could we get the slides, please? Okay, maybe I could also, okay. Okay, so here I've shown you now some adjoint correlator. So trace x of tau, x of 0, in the ground state of the one matrix quantum mechanics. So if we're talking about the ungauged model, that's all I have to say. In the gauged model, you should think of there being a Wilson line between x of tau and x of 0. Okay. In both cases, they are the exact same quantity. Okay. So that's the quantity we're plotting as a function of tau. And here's what I said. So the level 4 bounds are just a lower bound, right? So we saw that here. We just derived that log g is bigger than something. So that's the gray region shown. And then as we go to level 6, we get an island. So there's both an upper and lower bound, right, on trace x tau, x0. And we can go up to level 8. So there we get a very tiny island, right? And notice that I'm plotting this in log-log plots, right? So these islands are really quite tiny. Okay, so what can we do? So one thing that's a little bit interesting is that one can compute the actual adjoint gap in the...
I'm confused by something
Yes.
silly.
Yes.
The lower bound is getting worse? What's going on?
Sorry, there was only a lower bound, and then there becomes an upper bound. Maybe I didn't understand.
So, but the low...
The blue region is the allowed region. So it's the region between the upper and lower bounds.
Yeah, that's what's confusing me, because the lower bound of the blue region seems to be lower than the lower bound of the...
I haven't, yeah, so I've just overplotted it, so it actually
okay.
covers it up. Yeah,
Right,
yeah.
thank you.
Yeah, so one thing we can do is you can just fit a straight line. So a straight line on this plot would be some exponential decay, right? And you can, using the level 8 bound, you can estimate what that decay is. And that's an estimate of the adjoint gap in one matrix quantum mechanics. And it's possible to numerically compute, using some other method, the adjoint gap. And we can check that these level 8 bounds are extremely close to the actual numerical adjoint gap. Okay, so we can do this at various values of g. So here I've shown g equals 1. Another slightly interesting thing that we can do is we can go to negative values of g. So that's, again, this unstable potential that we talked about. There we can still compute the adjoint gap and compare. So, okay, so we can make a very similar plot also for the anharmonic oscillator. In that case, we can just do some exact diagonalization on the computer, of course, and we can compare, and we see that the level 8 bound is extremely close to the exact diagonalization result as well. Okay, now I'm going to the thermal case. So let's discuss that a little bit. So the idea for the thermal case is very similar. Okay, so the idea is the following. Well, we have these constraints. We can do one of two things about level 3. So, constraint number 3. So constraint number 3 only is true for the ground state. We could replace it with this energy inequality that we've been discussing, this EEB inequality. We have not done that. What we do is we essentially just throw this inequality away. We just throw it away completely, but we impose KMS conditions, right? So they should be equivalent. In practice, it's a matter of sort of pragmatics, sort of engineering which one is actually better. So far, what we've done is we just impose KMS conditions. So the KMS conditions can be written as a linear constraint on M, right? So we again have some M of tau basically equals some matrix times M of 0, right? There's some non-trivial matrix there because you have to commute operators through each other. But the KMS condition can be encoded just as another Lagrange multiplier. So you introduce some more Lagrange multipliers, you go through this rigmarole, and now you're using some splines that, so the splines go now between 0 and beta, and you're action that you write down also goes from 0 to beta. The thing you're optimizing is some t. So there will be some optimization function that depends on, well, some particular time t that is in between 0 and beta. And by a very similar kind of technique, you can bound the thermal 2-point function. Now again, we're inputting the state by using KMS condition, as opposed to using some inequality to input the state. And so I've shown a plot now for the anharmonic oscillator here. So what is this gray region? That's again level 4. And level 4 bounds, so actually, if you recall in this derivation, I didn't use ground state positivity. So this bound is basically true for the thermal state as well. In the thermal state, you have some shape, right? So you have a decaying exponential, but KMS tells you that you could also have the decaying exponential from, instead of going from 0 to beta, going from beta to 0, right? So you get the sharp bound, I mean a bound with a kink in it, but it's only for some trivial reason that this is the Z2 symmetric point, beta over 2. So this is the bound that you expect analytically. And indeed, you see the gray region we obtained using some spline methods. It's very sharp. The kink looks pretty sharp. So that's, again, I think, strong evidence that the spline methods are actually very good at even capturing some correlator that might have some sharp feature in it. Of course, it's not precisely sharp, but it looks pretty sharp just by eye. And then if you go up to level 6, well, you get a very tight island around the thermal solution. So the thermal solution, of course, is smooth at tau equals beta over 2, the actual solution, and we see that from the level 6 bound. Okay, so I've zoomed in on the level 6 bound here. And we're currently still in progress trying to use the exact same ideas to bootstrap trace x tau x0 for matrix quantum mechanics in the ungauged model. Okay, so in that case, we do not know actually analytically how to compute trace x tau x0 in the ungauged thermal one matrix model. So this method, we believe, should allow us to compute it. We actually have some lower bounds already, but we don't have anything production quality yet. So that is one application of these ideas for the thermal 2-point function. And of course, the eventual goal would be to do it in more complicated systems. Although, as I said, the ungauged matrix model is already supposed to be some very complicated model when you go to the ungauged sector at finite temperature. Okay, so I thought I would also, in the remaining time, just explain a little bit about Lawrence, McPeak, and Neal. So they are our predecessor.
Can I ask a
Yes.
What's the simplest matrix quantum mechanics where you might expect power law scaling at large n?
Yeah, that's a good question. I don't know the answer. Yeah. In particular, the only cases that I know of are basically, well, I don't know how to derive this power law scaling without having a gravity dual, essentially. Yeah. There was an interesting paper by Narevlansky and Maldacena where they discussed some, not exactly a matrix model, but some interacting quantum system that has some power law scalings. But it's not, that model actually turned out to be integrable, essentially. So it doesn't have strongly coupled physics, even though it has power laws. Okay, yeah, maybe I can say one more thing about this before I say the, yeah. So if you knew the thermal 2-point function, another thing you could do is actually try to extract the quasi-normal modes of the black hole at finite temperature. So there was these interesting papers by Matt Dodelson which discussed this. So you, just by knowing some features of the Euclidean 2-point function, you can actually back out of that some information about the quasi-normal modes. So the first thing you would like to see, well, we have a very concrete prediction for the quasi-normal modes in gravity, and it's somehow very non-trivial to see that there's quasi-normal modes just from the point of view of quantum mechanics, right? So, yeah, in case you're not familiar with this language, all I'm saying is that if you compute the Lorentzian 2-point function, so the Lorentzian 2-point function, let's say, of some operators, O tau, well, okay, OT, O0, in the thermal ensemble. Yeah. So let's say you compute, this could be in field theory, in any holographic theory, really. So this Lorentzian 2-point function, you might want to smear it out a little bit in Euclidean time so that this is not singular, but slightly smeared Lorentzian 2-point function, it has an interesting feature which is very basic, and that interesting feature is that it doesn't just oscillate, but it actually decays in Lorentzian signature. So it's obvious that it decays in Euclidean signature, but the fact that it can decay like some power here times t, this is related to the black hole physics, right? This is related to the fact that if you perturb a black hole, it will relax, okay? Another way of saying it is if you drop an object into the black hole, it gets absorbed by the horizon, and eventually the horizon becomes smooth again, right? So the fact that you effectively lose information in simple operators, a sort of concrete way of talking about that are the quasi-normal modes. So there's not just one of these things, but there's a whole spectrum of quasi-normal modes. And the interesting thing is that this number here is predicted from gravity. So you would like to see this somehow by calculating thermal two-point functions. Okay, now, yeah, maybe to say it slightly more provocatively, there has been some speculations in the past that even this one matrix ungauged quantum mechanics might have something to do with black hole physics. And one provocative thing you could say is perhaps you could wonder whether this model or perhaps some small variant of this model has quasi-normal modes. So I think that would be at least some qualitative evidence that there really is some black hole physics in this simple one matrix ungauged model. Okay, great. So I thought I would just explain in the remaining, I guess, 9 minutes, the work of Lawrence, McPeak, and Neal. And so in that work, which is a predecessor, they have a very similar method, but they're actually computing Lorentzian one-point functions. So here I've been discussing Euclidean two-point functions. There they consider Lorentzian one-point functions. So the one-point functions, the simplest context would just be an anharmonic oscillator. You put it in some non-energy eigenstate, right? You put it in some generic state, and then you calculate the one-point function at some later time, okay? So you assume that you prepare the state in a way that you know, right? You know the wave function of some initial state, and you just evolve that system forwards in time, and then you calculate some one-point function at a later time, okay? And very similar logic allows you to do this procedure. So there are some minor differences which I would just want to point out. So first of all, positivity here, we used reflection positivity. They instead used the same kind of matrix positivity that I talked about before, right? So they're talking about some Lorentzian one-point function, and they're thinking of that, so they just have some psi o I at some t o j at some t. So it's a one-point function. Okay, I've written two operators, but it's a one-point function in the sense that they're both evaluated at the exact same Lorentzian time. And this is some matrix, Mij. This thing is positive semi-definite, just using the positivity of this inner product, right? There's no... So this is one minor difference. Another difference is, of course, they input the state in a different way. So here we've input the state one of two ways. One, we input it by imposing the KMS condition. A second way is we imposed it by implicitly by using some matrix inequalities to tell you that it was in the ground state of the Hamiltonian. There they don't use that. So they just assume that you know the initial state. And what that means is that they assume that you know Mij evaluated at time 0. So because of this, that's equivalent to saying like they know the first few moments of the ground state wave function, right? Like they know, you know, x squared, x cubed, x fourth, x to the 10th in the ground state wave function, and perhaps some p's in there. But that's not the super precise way of specifying what the initial state is, right? Even in the simple anharmonic oscillator, if you tell me, you know, 10 numbers about the ground state, about the initial condition, that's not enough to specify what the full state is, right? So they get very weak bounds, actually, at large Lorentzian times. And I don't think it should be the fact that they get somewhat weak bounds at large Lorentzian times should not be interpreted as a failure of the bootstrap, but it's simply that they were not able to precisely input the initial condition, right? So there are many states that are consistent with the initial condition that they input. So it's not so surprising that as you evolve with time, the possible correlators that you could get very big. I mean, there's a very big region of allowed correlators. So just to sketch their plot, they essentially plot x of t here in some excited state. Sorry, it's the bad pen. So they take some excited state psi, they evolve it e to the I ht, and then they calculate something, let's say x, e to the minus I ht psi. Psi is not the ground state or any simple state. They calculate this thing. Well, the exact answer of the state that they had in mind is like this, but the bounds that they see quickly diverge. So they get something like this. And I think they interpreted it slightly pessimistically. They thought that perhaps the method doesn't work at very large times, but I think it should just be interpreted as the fact that there are many size that are consistent with the actual input that they provided. So I think the Euclidean setup is slightly more natural in that you can put in the state in a way which doesn't just involve specifying the initial moments. But here, for example, when we input ground state positivity, we're actually inputting ground state positivity for all possible times tau, right? All possible times tau between 0 and whatever time we're interested in. So we're actually putting in some sense, a huge amount of information about the actual state that we're interested in, right? For every time tau, you can perturb the state in some way, and the perturbation of that state has to increase the energy. That's what we put in. Okay, but another minor point is that you can actually kind of combine their Lorentzian ideas with our methods. So I perhaps don't have a lot of time to discuss this, but some generalization of this idea allows you to consider sort of mixed correlation functions that are partially Euclidean or partially Lorentzian. So I think it's kind of exciting. So first of all, there's two generalizations. They started with 1-point functions. We started with 2-point functions. There's a generalization to n-point functions, which proceeds along the same kind of ideas that I discussed. So one way of thinking about it is you can implement a quench at some finite time t. So you can just implement a quench by changing the Hamiltonian, right? And you could change the Hamiltonian just, another way of saying that is you could insert an operator at that particular time t. So by some variation of this idea, you can actually consider n-point functions in Euclidean time or even in Lorentzian time. So I think this is kind of exciting because in principle, a lot of the sort of dynamical questions that we're interested in these potentially strongly coupled systems could be addressed with this kind of method. Of course, I don't have results yet on what I just said, but at least conceptually, this method, I think, has some promise. So this is just, since the last Bootstrap meeting, I thought it would just be nice to end on an optimistic note about future directions that we could try to consider. So yeah, that's basically what I have. Thanks a lot for your attention. Yeah.
Questions?
Hi, thanks for the lectures. If I have a holographic CFT, should I be able to compare a thermal two-point function to this, and to what extent of precision?
Yeah, it's okay. The question is about, let's say, CFTs and thermal two-point functions in CFTs.
Yes, yes.
Yeah, so I think, yeah, it's an interesting question whether we can somehow combine some of these ideas in the simple quantum mechanical ideas to CFT ideas, right? So I think one sort of non-trivial thing is like, what is this equation in a CFT? It's not totally clear, right? So this is not an equation that, well, yeah, let me leave it at that. That's one of several subtleties for thinking about it. Yeah. Okay, for example, one could discuss positivity of the thermal two-point function when we do the, yeah, so maybe I'll discuss it offline. Yeah, thanks a lot. Yeah. Yeah, just to say it in one sentence, I would say some of these ideas about thermal positivity and so forth, I think have not really made it into the CFT community when we talk about thermal bootstrap. So just the two-point function on S1 times RD, right? You could wonder whether any of these positivities are useful for the bootstrap in that context.
There are no more questions. Let's thank Henry.
Which means that the CFT should have just Wilson algebra and nothing else. Because of this, the number of primaries would be infinite. There's no like algebraic way, integrable way of solving it. So the talk would be in two parts. The first part would be the field theory description. The second part would be some lattice model, which is basically what coupled anyon chains means. Okay. This is a pretty mixed audience, so let me review some like very fundamental things about 2D CFT. So for rational CFTs, we have the primaries. Usually we label it by phi. And they satisfy some fusion rules. Let's see, phi I times phi g is given by n I g k, phi k. And this n is the Valindo formula. So, and S here is the modular S matrix. It tells you how characters transform among themselves under the modular S transformation. So from this, we can basically work out the fusion rules for our primary fields. And let's take the easiest example, which is like the Eason model. We will have like sigma times sigma goes to 1 plus epsilon. Epsilon times epsilon goes to 1. And the third one is like sigma times epsilon goes to sigma itself. This we are all probably very familiar. Probably something that is a little bit less familiar is that in two-dimensional rational CFTs, there are a set of operators which are called topological lines. They are also labeled by the same primaries. So if I have a topological line, I can denote it as the line epsilon, and I can merge them, the two of them, and what you get is a line, but this fusion follows the same fusion rule as the primary fields, okay? So you can just read from there, epsilon times epsilon should give you a line which is labeled by identity, okay? So these are like the symmetry operators of your CFT. Remember that if we are in D dimension, the symmetry operators is a topological surface, which is the codimensional one, and therefore you can ask how many like charges are in this codimensional one surface or not. You can change it topologically as long as you don't encounter something local. It's safe to move them. So it's the same thing here. So we are in 2D, so therefore the topological objects are like one-dimensional, and they are just the topological lines. One can basically. Sorry.
Oh, question.
Yes, please.
What is the relationship what's the definition of the topological line? So 1 of epsilon, what's the definition of it?
These are just operators of your CFT system. It's topological means that you can freely deform them. So if I have a circle, I can ask the expectation value of this thing. Topologically means I can freely deform it. So these are like classified by CFT methods. And maybe let me see that from this fusion rule, you can basically understand what they are. For example, this epsilon line, epsilon times epsilon gives you identity. So this epsilon is basically the Z2 symmetry objects. Epsilon corresponds to the Z2 symmetry of your Ising model. So, but on the other hand, identity is the identity element of the Z2 group. But what is a bit less familiar with is the sigma. If you multiply 2 sigma, what you get is one line that corresponds to identity. But in addition, there's another line which corresponds to epsilon. Yes, so these are, mathematically speaking, these are fusion categories. They need to satisfy certain Pentagon equations and so on. But the point is that these are, I hope some people are familiar with this. These are called Valindo lines, has been classified, started in CFT for a while, and people know how to fuse them. They form some tensor category, okay, fusion category.
Maybe just a kind of a classification answer to that question. I mean, you can just think of this as defined as line operators that are topological in the sense that you can query function are invariant if you deform the operator without passing any other operator. And topological lines are more general than Verdinda lines, but the Verdinda lines are very special. They happen to be in correspondence with primaries of the rational.
Yes, so just to add to what Xing said, this is not all the symmetry, because as you can see from the fusion, it's like it's abelian, so it's commutative. So the symmetries, CFTs can have more symmetries, which is non-abelian symmetries. But let's come back to this line. This line is not a group theoretical type of line. So if you have a group theory type of symmetries, these lines should carry arrows, but for our talk, we don't care about the arrows for the moment. So if I have two groups, I have a group G1, element G2. So if I fuse them, if it's a group-like symmetry, I should get something like looks like G1, G2. So they're just one single element on the right-hand side. But you look at this line, this is not a group-like object. So that's why it's usually called non-invertible. We will be talking about something called, we will be focused on these non-invertible symmetries because it's very useful. In fact, if you think about the transverse field Ising model, you have the Hamiltonian, which you can write as sigma I, G, sigma x, I plus 1, plus, let's see, H, sigma z. Very roughly speaking, this is not precise. There's a duality called Gram-Schreiner duality, which exchanges these two terms. And when you try to when you have a coupling constant that is different from each other, these two numbers are different, you are breaking this Gram-Schreiner duality. But if you try to preserve this non-invertible symmetry on the lattice level, you will be able to reach the CFT point without any fine-tuning. So this is an example, like in the transverse field Ising model, H over G equal to 1. You put it on the lattice, makes lattice bigger and bigger, and you run the numerics, you find that your ground state is the CFT ground state. That's because you preserved this Gram-Schreiner. So one theme of this talk is basically that we want to preserve as much symmetry as possible so that the CFTs we are targeting would be a stable phase of matter. In fact, this new CFT we are proposing now is stable under some non-invertible symmetry. So we talk about the Ising fusion category, so Ising symmetry. And another thing that is important for us is the so-called Fibonacci symmetry. In this case, again, the lines, let's call it W, and the fusion rows are basically W times W goes to 1 plus W. Okay, you probably would recognize this is the symmetry, the fusion row of Liang singularity. Okay, so the CFT we are going to play with would be two copies of tricritical Ising models coupled together. So the tricritical Ising model has both the symmetry of the Ising category and also the symmetry of the Fibonacci category. And I think, in fact, you can ask, how does this topological object act on your local operators? So I have a phi I have a topological line, I call it dA. It's again given by the same S matrix of the S transformation matrix. So basically, I can write something like dA acting on phi I as a state, which is given by SAI, S0I on my state. Okay. So just from the S transformation matrix, you can look at how these symmetry lines, non-invertible symmetry or invertible symmetry lines, acts on your local primary fields. So let's make a table for the tricritical Ising model. So we will care about this Fibonacci symmetry. And I'll call it W. And this is the scaling dimension of that operator. Identity. This is minus psi to the minus 1 over 5. Sigma prime. No, sorry. This is epsilon sigma, sigma prime, epsilon, epsilon double prime. These are the field content of the track-critical Ising model. And we look at how the Fibonacci line acts on the local objects. Epsilon, yeah, sorry, there are one more. So these are the these are the Z2 even operators of the data. I see. Yes, I should be. This one should be epsilon prime. This one should be epsilon double prime. We don't have this one. Okay. So psi is the golden ratio. Okay. And epsilon prime is this one. Epsilon double prime is psi. And this guy, 1/5, 3/40. And 7/8, 6/5, and 3. So suppose I am able to build a lattice system which preserves both the Z2 symmetry and the Fibonacci symmetry. And you can look at what's the leading operator environment under. Sorry? The first row is how this W acts on the local operators. Times the number, which is basically this number, okay? And if we try to preserve the Fibonacci and the Z2 symmetry, you look at it, first the sigmas does not work, and the leading one, notice this number is psi, this number is also psi, so the topological lines acts trivially, non-trivially on the vacuum, so it has a number. So you should divide this number by this number. So you can see that the leading operator that is invariant both under Fibonacci and the Z2 symmetry is the epsilon double prime, which is an operator with scaling dimension equal to 3. So this tells us the tri-critical Ising model is stable if you preserve both Fibonacci and Z2. Because of this, and in this paper, people wrote down a lattice quantum Hamiltonian, which allows you to reach the tri-critical Ising model without fine-tuning. So it's an anyon formulation. And in the second part of my talk, I will talk about how to build this lattice. Hopefully, we could reach there. Yes?
I'm probably just going to ask you to explain what you already explained, but a bit slower. So you explained first that H equal J in the Ising model was to preserve this low high temperature duality, right?
Yeah, Gram-Schreiner duality.
Right. And now this is a generalization of that for tri-critical, where you need to use one more symmetry, right? So can you just explain it, repeat
We need to
again
use both the Fibonacci, which is this W, which is what I explained here. This is, again, a non-invertible symmetry. And we also need to preserve the Z2, which is, because tri-critical Ising has a Z2 global symmetry. Okay. You seem confused.
No, when you say I explained here, but then you pointed and there's only a simple equation, W times W. I think I missed probably what words you said when you wrote that Fibonacci equation. What was that?
Which one? The numbers here? Okay. So sorry, it's a bit scattered here. So here I was explaining how this topological operator acts on local objects and how they transform. So I'm basically using this formula to derive that table, and which tells me whether my local operators are stable or unstable, whether are commuting or anti-commuting with the symmetry or not. So from this table, you can read out that indeed there are only two operators that are commuting with the symmetry. So if you write a lattice system preserving Fibonacci symmetry, it's like you are deforming tri-critical Ising model by these two operators, either of these two. But if you, in addition, preserve the Z2 symmetry, this guy is disallowed. So there's no relevant operator allowed by the tri-critical Ising model, so that's why it's stable. Sorry? Yeah, you really need to divide this number by this number. So it's like I have an operator inside, I pull it out, it needs to be an operator like this. When you shrink this, it's like acting on the vacuum, so you get this number.
I also have a question about this. So I understand that if you just take an operator and you surround it, then it's fine.
Yeah.
But don't you want to ask whether you can move the line past this operator? And in that case, you have to not just surround it, right? Because W is W. If you use this into 1 plus W, you also need to ask, is there some sort of like W tail which is going to be stretching out from this operator?
Yes, go ahead.
I mean, you can bootstrap it. You can prove that if this thing has the same eigenvalue on operator as identity, then there is nothing else. But in general, you're absolutely right. We go through, there will be another W line connected to a defect operator.
Yes.
This is quite general. Essentially, certainly in the case of unitary theories, you can easily argue this from unitary. Just if you have anything else, it's going to break.
I think it's a good point to mention this reference. So if you want to learn more, please read this reference. I'm just basically giving the most basic information about this fancy topic of non-invertible symmetry and so on. So now let's look at our field theory. So we basically want to find a flow that deforms tricritical Ising model and preserve a certain number of symmetries. So the theory we are going to consider is basically this. An action would be written as A equal to 1 to n. I'm writing n copies of tricritical Ising model. Just schematically, this is the CFT action. But I want to deform it by a coupling which is called K, dx squared, sigma prime of the A copy, sigma prime of the B CFT. And I want to sum over A not equal to B pairs. Okay. So you can look at what's happening. In this table, you already noticed that the sigma primes commutes with the Fibonacci. So the symmetry of this system would be n copies of Fibonacci, but I'm summing over an not equal to B pairs. Therefore, there is a Sn symmetry, X on this. Also, there's a global Z2 that is preserved, because you can change the sign of this sigma by to be the minus sign of it, and therefore the whole symmetry is going to be direct for Z2. I'll call this guy C. It's really a section in that paper that I read. We started to think about how to do it numerically, and in the end, we found something a bit surprising. So what is surprising? We found a CFT when it's n equal to 2 case. There's a CFT with central charge equal to 1.151 plus or minus 0.001. This number is from the fitting of the entanglement entropy formula, some formula to calculate the central charge. So I think it's better to treat it as kind of an upper bound, meaning that this is my lattice is not infinite size. So this error is a fitting error, but there could be also a finite size effect which could make it a little bit smaller. I don't know how small, but this should be pretty close to the true value. This is just a disclaimer. And also, another thing is that it's stable under this C symmetry, which I denoted here. So stable means that literally on the lattice model, we found a stable phase. We found a CF conformal phase. So you tune some coupling, you get the same central charge. So there's no relevant operator that are invariant under this symmetry. Okay. So then why do we conjecture it's non-rational? It's because this central charge, as you can notice, is quite small. So you could basically look at the rational CFTs that people have constructed and compare with it. So what are the CFTs has similar central charge? First of all, maybe it's a strong finite size effect. It could be a minimal model, but it couldn't be a minimal model because the symmetry is Z2 times Z2. There's no minimal model with that symmetry. Second, for C equal to 1, there were some papers claiming there's no Fibonacci for C equal 1. I don't know whether that's a proof or not, but it looks like it's very hard to get Fibonacci symmetry for C equal 1 CFTs. And what are the ones after that? One of them has C equal to 8/7. This is the Z5 parafermion, the bosonic parafermion. The bosonic wording is a coset SU2 level 5, mod U1. This guy, if you look at it, it has D5 symmetry. So first of all, we don't find any Fibonacci here. Also, if you just look at the global symmetry, it's D5. D5 cannot contain both Z2 times Z2. So that's basically one thing. The next one you get is C equal to 81 divided by 70. This is the coset, which has this form, times SU2, level 3, mode SU2, level 5, okay? This guy do have one Fibonacci symmetry, but it doesn't have two. Also, I think later I will show that in our calculation we could find the degeneracy of states. This is because of this symmetry. It has degeneracy of states. And if you look at the spectrum of this guy, there's no degeneracy, okay? Sorry, I forgot to put the number here. This guy is 1.14-ish. This guy is 1.157, blah, 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 blah. So you see, it's already higher than. Which one? I don't know, because we are doing the bosonic one, so because our theory is bosonic, right? So the next one, maybe.
Actually, can I ask you about the second example? When you speak of comparing the degeneracy, I'm wondering whether there are other modular invariants can form out of the W algebra.
Yeah, this one I think we checked. There's just one bosonic border invariant. Next one is actually already C equal to 1.2. C equal to 1.2. There are two models here. One is tricritical Ising, tensor product of Ising. This guy has 1.2 because this guy is 0.5, 0.7, so it's 1.2. But it also doesn't have the right symmetry because the Ising part do not have the Fibonacci. Actually, another one is a W3 minimal model. Okay, but again, this one has S3, so it's not enough to contain the two of them. Okay, so I think that's all we did. First of all, there's no classification of rational CFT yet, so we don't. This is like a constructive comparison, enumerative thing. That's why it still remains as a conjecture. Okay, so. I also want to mention another theory, which is mentioned to us by Yifan, which actually would play some important role later. The next one is C equal to 1.35. What you get is SU2 level 3 times SU2 level 3 mode SU2 level 6. This guy actually has the correct symmetry. Why does it have the correct symmetry? Well, you need to check it explicitly, but one way to understand why Fibonacci appears is because of the Furon-Rose SU2 Western minimum model is following the production role of SU2 spins. So you are getting, you are getting what you get, but to be specific to the G equal 1 case, what you would get is 1 times 1 goes to 0 plus 1 plus 2. But when you have k equal to 3, G needs to be smaller or equal to k over 2. So the 2 cannot exist, so it disappears. So each of this gives you a Fibonacci. There's a Z2 permuting them, there's another Z2. So it do have the correct symmetry. You have to make sure that all these symmetry lines survive under this quotient. So we did that check. So it looks like this is a good theory. It's indeed plays some role in our analysis, but I want to mention that there is a relevant operator which has dimension 33/2. So this theory is not stable, okay? Even though it has the right symmetry. I think it's safe to conjecture that if you deform this theory by the operator, it would flow to the CFT we discovered, okay? That's field theory already. Now I think it's a good time to move to lattice model.
Have you considered the 1/n expansion of that fixed point?
I see. It's an important comment. You need to plus irrelevant terms, which will become clear later. So there's no, you cannot do 1/n expansion of this one. It will become clear in the end of my talk. So
sorry, maybe I'm not understanding the definition of theory. I thought you're starting from the product tricritical Ising and then just to turn on the relevant definition.
This is true, but we are going to build a lattice model. Our lattice model is not, when you deform it, the lattice model is not clean enough. So if you do the analysis clearly, do the analysis carefully, you would notice that the deformation you are adding is both this one and some irrelevant terms. So, okay, I think we are in the field theory part. Let me mention that there is a paper by Leclerc, Ludwig, Masato in the early days, which basically said the NCO2 case, if you deform by sigma prime, it's integrable, it flows to a gapped face. So they did this analysis already. So our lattice model, it will become clear later, but it corresponds to deforming this CFT by both relevant and irrelevant deformations. So it's a different.
Purely in field theory terms. So first of all, just to clarify, you are not claiming that there is RG flow from the product tricritical.
Yeah, it's not even complete that flow. But
regardless of that, so if I just want to know whether there's RG flow from the tensor product 2-copy tricritical Ising to the new theory that you found, you're not claiming that's source.
I'm not claiming that. So maybe it's a good time if I just write what is the conclusion for us. So the horizontal axis is the sigma deformation. Vertical axis is like epsilon, I think it's epsilon double prime 1 plus epsilon double prime 2 deformation. And you can look at this space. This flow is integrable, okay? And it flows to a gapped face. And our numerical simulation, as I said, the deformation is not clean. So you are really deformed. Okay, sorry, here is M2 times M54. It's a tricritical Ising, 2 copies. As I said, our deformation on the lattice is not clean enough, so we are like moving towards a specific direction here. Okay, so there's a separatus. This is the CFT we discovered. There's a separatus separating these two faces. And you can ask what happens at the separatus. But we have a CFT that helps us. So this is this CFT prime, which is this one. That's why I said it's important. So this guy has a relevant deformation which preserves all the symmetries. So we have a CFT prime living here. It has a relevant deformation, either drives you to the CFT we discovered or drives you to the gapped face. So you can complete the RG flow using your imagination, but this is basically it.
Sorry, I'm a bit lost. What is, you were talking about field theory description of this flow. What is the field theory description of this flow? You're saying that on the lattice you have epsilon, but I don't care about lattice. I just want to know the continuum description. What's the continuum description?
The true field theory description, if you worry about UV completion and so on, is a flow from here to here. This is UV complete. It's there's no like it's deforming a minimal model. It's deforming this model by some relevant arbitrary flow to that one. But what I'm doing here is that my lattice corresponds to moving towards this direction. These flows are not because it has irrelevant directions, right? So
yes.
So therefore, these flows it's completed by lattice, but not completed by
but
by the field theory.
Sorry, but
yeah,
I just don't understand in what you began by writing this Lagrangian sum of critical easings, then adding this deformation, and from the RG diagram that you're drawing, theory is completely irrelevant for this fixed point.
I wouldn't say it's irrelevant because this is still an effective description of the lattice model.
Flow that connects CFT or CFT prime to
Federal.
Sorry?
Is your mic on? Yeah.
Yeah. Do you want me to be louder?
Yes, please.
Yes. So can you please show us, or show me, because I'm not missing this, is there a flow from CFT or CFT prime or back? Like, is there any RG flow connecting two critical easing models?
No, there is a flow like this, but this guy is not touching the thing. It's not touching the UV.
So there is no such flow.
Yeah. So,
Okay.
so the flows that reach the reach the infrared CFT is described by this as a UV with some irrelevant terms, which in this case by is sigma prime, epsilon prime, epsilon prime. This flow is not good because it's not UV complete.
Yes, I understand.
Right. So
Yeah,
so
I'm
but
just
still,
trying
I think
that-
around here you can use this effective theory to see it. Right.
Yeah, I'm just trying to understand what was the point of talking about.
So let me emphasize. We do the lattice calculation. We make sure we preserve this symmetry. And that's all we got. Then the other things are like interpretation using field theory or using whatever you have.
Just trying to clarify the actual field theory statement. So if I want to understand analytically this flow from CFT prime to the new CFT, I suppose you could try to do 1/k expansion for this SU2k times SU2k.
Yeah, that's one possibility we didn't do. Yeah. I think that might be a good thing to try. So I think I still have half an hour, so let's move on to field theory description.
Hi.
Yes, please.
Sorry. Maybe I'm confused about something simple, but this CFT prime, you said it only had one relevant operator?
Exactly.
So
One relevant operator under that symmetry. Under
I
that
see.
C symmetry, big C symmetry.
Oh, so there's another relevant operator that if you turn down would flow to the gap phase.
Right.
That
So
would
when I was giving this practice talk, there was a very good question asking whether I can do TCSA to go from here to here. It's a very good question, but this operator preserves the big non-invertible symmetry. So you have to regularize it in a way that you preserve that symmetry. I think that's a good direction to explore, actually. Okay, so let's move on to the lattice description. So lattice model. So my local Hamiltonian, my local Hilbert space is given by plus or minus. It's a bit. It's like spin up, spin down. And my Hamiltonian, let me write it down, is given by +1 plus n plus 1 plus, okay, -1 minus n I minus 1 and +1 psi. The golden ratio is appearing again, sigma x plus -3 and I plus 1 plus psi minus 1. Okay, and you need to have a repulsive term to be like this. U and U has to be much larger than 1. Let's see, much larger than 1. So, sorry, my Hamiltonian is GHI. My HI is defined as this. So you can see it's a very naively looking Hamiltonian. It's a spin written as polymatrices and nothing fancy. The only fancy thing is this repulsive term, which, sorry, I forgot to tell you what is N. N is the projector onto the spin down state. So the role of this repulsive term is to give some local constraints to your Hilbert space. so that spin up and spin up cannot be nearest neighbor to each other. Okay, so this is you have to set a very large repulsive interaction for the spin up and spin up. Other than that, it's basically some polymatrices and so on, and it's just the golden ratio is appearing in the Hamiltonian. That's why people sometimes call it the golden chain. So. But this Hamiltonian has an interesting interpretation in terms of the fusion of anyons. So you could just reinterpret it as some the fusion sequence of some anyons. On each of these lines, you put a W particle, and you read from left to right. If you have a W particle here, and you fuse the two of them, you go to the right, and what you can have here is 1 of W, because of our fusion rule, which is W equal W times W goes to 1 plus W. Okay. But on the other hand, if you have a one state here, you fuse it, this can only be W. This explains the constraint why one up and up cannot be next to nearest neighbor to each other. So this guy is equivalent to 1 particle, this guy is equivalent to W particle. Okay? So the local constraint basically tells you that your states can be reinterpreted as a fusion of anyons, and they follow this rule. Okay? And we talked about the topological lines, fusion category, and so on. In fact, if you look at the Hilbert space, you can do a change of basis. Okay, the W particle, I minus 1, x I plus 1. So on each of this bound, you will have a two-dimensional Hilbert space, but with local constraints. You can use the so-called F move, because there are some specific fusion categories. You can use an F move to change the basis of this Hilbert space. What you are getting is something so this is called F moves. So if you have some topological lines fused in this way, you can do some so-called F move to re-express it as this kind of topological lines. Okay, and this F is something specific to your symmetry. So we are talking about the Fibonacci symmetry, so we know what it is. It's just some numbers which people can calculate. It's specific to the symmetry you are talking about. So, but to look at the Hamiltonian, to look at our Hilbert space, this is basically a change of basis, but you do the change of basis using these F symbols, okay? So this is like the 3 nearby Hilbert states, and you change the base, you interpret it as this kind of fusions, okay? And what this Hamiltonian do is to favor the states, this is in a new basis, is to favor the states where x prime is equal to 1. This fusion line is equal to 1. So you can see we take 3 nearby Hilbert space, we change the basis, we have a basis for different states. They correspond to either x prime equal to 1 or equal to W, but we favor those ones that are in the W, in the 1 sector. Okay. So this is so basically this Hilbert space, this Hamiltonian, this lattice Hamiltonian, is built in a way so as that engineered so that you can preserve this non-invertible symmetry, this W symmetry. And this actually, if you put this on a DMRG calculator and you just run it, you find that you get the tricortical Eaton model just as the ground state. Okay. So I need to mention that.
Sorry, just understand. So far, this is just tricritical.
Yeah,
just
so
one
this
tricritical.
yeah, this is one chain. So we are going to couple them together, step by step.
Okay. And you were explaining that this repulsion, by the way, it's I plus 1, right, in the second term?
Yes.
that this repulsion was related to the fusion, the first picture on top,
Yeah.
where you had 1 W. What would you put on the next line?
Because 1 and W, sorry, I didn't write it completely, because 1 times W can only be W, right?
So that I understand, yeah. But in the next line, what would you put?
All of them you put W.
No, in the bottom, in the bottom. You have 1, W, and the next line. No, on top. On top, you wrote 1, then W.
W,
No.
W, W, W,
No,
W,
no.
W, 1 W?
Yeah, what about the next segment?
Next segment, you can be either 1 or W.
Yeah, that's what I'm confused, because and then you mentioned something about repulsion. Are you saying that out of that 1 and
So
W,
if
you
I
kill
find a
one
1, my nearby one has to be 1. That's the only thing. If I find a W, next one can be anything. So it's just 1 and 1 cannot be neighboring.
Got it.
That's why I'm saying here 1 and 1 cannot be neighboring.
Okay.
So in principle, one should try to develop a way to treat this kind of local constraint hero space using DMRG. I don't know how to do it. It's just I'm not a numerical expert. I think it's a good time to just say that we did this calculation using DMRG, density matrix renormalization group, which is a very efficient way to calculate spin chains, to give you the ground state, first excited state, and so on. Nowadays, there's already like well-developed packages that you can just put in the Hamiltonian, it will calculate it for you. It's a black box for me, and it's very efficient. So if you don't know how to use it, it's good to ask AI. And all the result I'm presenting, I think if you talk to AI and try to use iTensor, you can reproduce it in 1 or 2 weeks. Okay, so it's really nothing fancy. I won't give you the details because I don't know how to do the numerics, the details of the numerics. It's a black box for me also. But let's study this one chain Hamiltonian. One question you can ask is, where is the Z2 symmetry? In fact, the Z2 symmetry is realized in a very interesting way. So in this seminal paper, they started this system clearly, started this system. And this is the momentum. Vertical axis are the energy, but we will rescale it. And so that you can use it to get the scaling dimension of your operators. What they found is a comb, and this is a momentum pi. So what they realize is that the states, the low-lying energy states, are scattered either at the momentum 0 or at the momentum pi. For here, you find something at the ground state. You find something at 1/5. Is that correct? Yes. Well, for here, you find something at 3/40. And you find the descendants here, and so on. So what I'm trying to explain here is basically saying that the Z2 symmetry of this transverse field, of this tricritical easy model is not built on the lattice level. It's realized as a lattice translation. Because this is a momentum pi, what you are having is, you can see that your order parameter is really -1 to the I. And as you shift this side by 1, I go to I plus 1, this sigma goes, changes the sign, okay? So this basically tells you how you can identify this sigma operator in this calculation. So what we did was basically consider this one chain Hamiltonian and deform it by a staggered deformation. This is for one chain, just to make sure that we are doing what we want. So your Hamiltonian, you can write a new Hamiltonian, which is basically sigma I, G, Hi. The Hi is the ones I was mentioning. But you could add a deformation term. You put a -1 to the I, Hi. Okay? So my H is Hamiltonian density is built in a specific way so that it commutes with the Fibonacci symmetry. I'm adding this staggered deformation so that it's odd under the lattice shift on one side. So in the end, what you found is that you can use this to calculate, so roughly speaking, my I should be identified as sigma prime. You can do something similar. For example, what do you identify as sigma? You can basically measure -1 to the I, some polymatrices. It doesn't matter which one you choose. In practice, we chose the Z. You can identify as sigma. Because this guy commutes with the Fibonacci, this guy do not commute with Fibonacci, so this is the leading one that do not commute with Fibonacci, so you get this. You can just study this model, and when H is much larger than G, what you get is two ground state. You can measure the sigma expectation value. One of them is 0.3, another is roughly speaking 0.9. Okay. So you see it has degeneracy. The ground state has degeneracy, but it does not have the explicit Z2 symmetry because the expectation value for sigma is different. So Z2 is explicitly broken, and Fibonacci is spontaneously broken. You found two ground state. In fact, if you start from tricritical easy model, you deform it by sigma prime. This flow is also integrable. It's gapped. People know that it has two gapped ground state. So now we can just basically couple the two chains and look at the model we are doing. So we are starting.
Just to be sure, you want to put a -1 to the I in the sigma prime identification as well, or no?
No, this sigma prime, yes, sorry. Sigma prime, -1 to the I, yes. Right, so then the coupled chain is basically Hamiltonian like this. These are the decoupled limit, but you put a k term, which you deform by h1i, h2i. This is how you couple them. As I said, we identified this h as the deformation corresponding to the sigma prime, so therefore we couple them together, couple two different copies together. This is what you are getting. In the end, we started this model using the MRG and found the CFT we were caring about. And I want to mention that if you look at this term, you notice that the Z2 translation, the Z2 symmetry for each of the copy is explicitly broken. Because if you just change the first chain, I go to I+1, this term is not invariant. But it's invariant under the spontaneous shift of both of the chains. So this I go to I+1, I go to I+1, and this term is invariant. So this term explicitly breaks the symmetry of Z2 times Z2, the first copy, the second copy. It explicitly breaks it into the Z2 diagonal. Z2. Because it doesn't preserve the independent translation on both of the sides. Okay? Yes, you need a repulsive term for all plus repulsive. Okay, so I have 10 more minutes. Let me explain some of the tools
Just
go ahead.
Very quick summary. So the first blackboard, it's a critical CFT without the need for any tuning, like in the Ising model.
Exactly.
Then in the second blackboard, we perturb by sigma prime and we flow to some gap phase.
This is
and the flow presumably is integrable.
Exactly.
And then the third blackboard.
The field theory is integrable. The field theory is integrable. This model is not. So
the field theory is integrable. Okay. And the third blackboard is under construction.
Exactly. Yeah, it's interaction. So we just started this model, and I need to introduce some tools. First, there's a package called iTensor. It's to do tensor contraction and so on. But in this I tensor, there's a function called DMRG. So you can just quote it, and you would be able to do the calculation. Second, we are going to consider a periodic chain with length L, and we can define reduced density matrix by taking a small segment. And from this small segment, we can build the reduced density matrix rho, and then we can calculate entanglement, which is given by rho log rho, and take the trace. Okay. All these you can just code it up and do the calculation. For a CFT, what you expect is the entanglement entropy scales like this: the central charge over 3, the log of something called conformal distance, which I will explain later, but there's a constant term. This guy is not universal. It's depending on which model you study. This LC, people call it conformal distance, but it's really expressed as this, L over capital L times the pi. So it depends on the size, small l, and size bigger L. So you can just calculate the entanglement entropy as you change the size of this segment and fit against this formula to get your central charge. I think this is the most efficient way to calculate the central charge for quantum system, at least. And there's another tool, which is that your energy for excited state and ground states should scale with the size of the lattice as this form: 2 pi velocity over L times delta minus C over 12 plus higher order corrections. Okay. So from this, you can basically map the energy of your states onto the scaling dimensional operators. I should mention, importantly, there is a Z here, which is telling you the dynamical critical exponents of your system. So we did do a check for our CFT point by plotting basically the ground state energy over L and the size 1 over L. You see a very good linear relation in our system. This is reported in our paper. You can just take a look. So that basically tells you the dynamical critical exponents is equal to 1. So this CFT is Lorentzian symmetric. So because we are doing a lattice model, I think it's very important to check this, because you can get like Lifshitz fixed point or other things. But we did a check using ground state, scale it with respect to the lattice size, and you get a C equal to 1. You get a Z equal to 1 critical system. So it's a Lorentzian symmetric. So let me just report a bit what we had. Yeah, we can skin the central charge with respect to this coupling K over the coupling G, which is K over G. And on the negative axis, it quickly drops to 0. So this is the gapped state that people discovered by integrability. On the positive side, you go this, and then it flattens out quickly. So that's why I said this is the stable phase, because I can change my coupling as much as I like. The central charge doesn't change, and the conformal data doesn't change. So this is the stable phase. That's why I said the system is invariant under, is stable under that symmetry. Yes, please.
K equals 0, do you reproduce the expected?
Yeah,
value
you
of
get
the
1.4.
central charge? 1.4? Yeah.
Roughly. So I want to mention one thing. So we can basically measure the central charge here and measure the so-called effective velocity speed of light, because you are on the lattice. The speed of light is not necessarily the true speed of light. Measure it here, and you use this formula to get the leading few spectrums. So we got a spectrum, the first few. Turned out they are all scalars, which is not too surprising. But you find some of them, again, scattered around momentum pi, some of them and momentum 0. We can also look at how do they transform under this Z2 permutation symmetry. And you find the ground state here, you find another one, you find the degeneracies. And here I think it's more like this, a dot, and maybe a circle. Circle is a Z2 permutation, even. Sorry, this is odd. The dot is Z2 permutation even. Okay. So you should ask whether my symmetry C acts non-trivially on my infrared, on my states or so on. But this degeneracy is basically because of the Fibonacci square times the Z2 permutation part. Remember, my symmetry is Z2 times Z2. If I don't have this non-invertible symmetry, Z2 times Z2 has just one-dimensional representations. There's no, you shouldn't expect degeneracy. But because of this one, it could have degeneracies, and it's showing up in our spectrum. So I think it's safely to say that indeed the system has the symmetry, which is given by this one. Yeah, so I already draw the RJ diagram. So I want to see, just to comment on the RJ diagram. It's because I'm deforming it by this one. My HI has both staggered and unstaggered part. The staggered part would be sigma prime. The unstaggered part would correspond to epsilon double prime. So that's why I said my deformation is not clean. So it corresponds to moving towards one specific direction in the RJ diagram I drew earlier. So that's why I give that interpretation. In principle, this is still a conjecture. Yes.
Sorry, why couldn't you say that there is -1 to the I square, multiplying those two terms?
But it's also the production of the ones without -1 to the I. So it's like a Fourier transformation with the zero, the mode at the momentum 0 and the mode at the momentum pi are both appearing in this specific interaction. So this guy really should be identified as sigma prime 1, sigma prime 2, and sigma prime. Yeah.
I don't understand. What lattice version would you write if you wanted just sigma prime times sigma prime?
You would need to add some more terms, which is you would need to add next to nearest neighbor couplings for each of the chain, and you can use the anyon formulation to write something that corresponds to sigma primes, and that's actually what we plan to do later, basically to skin this two-dimensional space and to confirm that phase diagram. But this interaction itself is not clean. It's mixed coupling. So I mean, it's not really. So HI, roughly speaking, would contain both modes at 0 momentum and pi momentum. So what you are getting is like identity plus epsilon double prime plus like -1 I sigma prime. So you plug that in, do the summation. You notice it's deforming by sigma double prime and sigma.
I'm just still trying to understand the relation to tricriticalizing, because so you said that you need to add some irrelevant deformations, right? But there are infinitely many irrelevant deformations. I'm just asking why you're saying it's like specifically epsilon double prime and.
Yes, that's approximation. We are adding some irrelevant deformations invariant under this Fibonacci symmetry, under this all symmetry.
And what is the full symmetry that you preserve in the lattice?
The full symmetry is this one. This one is emergent.
Sorry, and that Z2 one, the last one, which one is it? Which Z2 that is?
Sorry, say it again.
So which Z2 is emergent?
The one that flips sigma 1 and sigma 2 of the Z2 spin.
Thank you.
Okay. I think this is pretty much all I want to see. Let me just see a bit future directions. One thing as already anticipated is that Can I have 2 minutes? 1
Can I
minute?
ask a question? I didn't quite understand the logic here. I wanted to ask about, maybe you were explaining this and I missed it, but the scalars, can you see explicitly that they're charged under the W symmetry, which prevents them from?
You can check, but we didn't do.
You didn't,
We
but you
didn't do.
could.
But
There's a way to do that?
There's a way. I mean, because this topological symmetry is basically you can write them as a matrix, explicitly on the lattice level. You can just check how they transform its states.
And you also have some understanding as you dial K that you should move down to 2 coupled tricritical easings.
Right. So
there
this
you
is
know
like
what all
the
operators
crossing.
are based
Sorry.
on there you know all the operators and how they transform under. You could sort of follow them as you dialed. K,
Yeah,
follow this
that's
function.
in principle possible, but this calculation we are doing is already very heavy. So in the end, we checked 1 point. Well, for you need to set the number of bound dimensions in the MPS approximation. For this plot is obtained by lower number of bound dimensions. For high bound dimensions to calculate central charge and everything, we just checked 1 point.
Do you know what the dimension of epsilon prime prime ends up being in your theory?
This one?
Yes, because that's the one that's the leading irrelevant.
No, we
operator you
didn't
could
reach that because this you can actually. There was another nice question that people asked me: can you check the algebra, right? Shall check the Wilson algebra to make sure that you are to pick a good point that corresponds to your CFT? The point is that this MPS calculation, you have to do it step by step. You don't. The maximum we reach is still below 1, so we don't have any current. There is a algorithm called the PUMPS, which is periodic uniform MPS, which but I'm not an MPS expert, so we didn't check that.
I have one last question, which is you have computed this entanglement entropy as a function of L for several values of the size of the system. Couldn't you extrapolate in the size of the system? The number you quoted at the beginning of your talk, 1.151, was the
was the final bit. We did the fit.
But don't you get a better estimate if you calculate at many different values of the system size and extrapolate?
If you use smaller system size, you plot all the curves, they overlap. For small system size, it only depends on this combination. So even if you do small system size, your curves overlap. So it's really the biggest one that it's important. You are right. We can probably, in principle, consider fine size effect. That's one thing to do.
In the plot in your paper, it looks like the curve is slowly turning over just a little bit, but still
yes,
visible
so it's
as
like
you increase the system size. So
yeah,
it seems like
so I think would be have some fine size effect. This curve we are looking at is convex, so it's so that's why I was emphasizing that the number we are getting probably are still like still running. But
it just seems like you could say a more precise statement than that it's still running. You could say how much it's changing, and you could extrapolate.
Yes, that we should do. Thank you.
Thank you.
Okay, so first, I want to see that this. Can I have 1 minute? Yes. I want to see that this anyon formulation, basically the plot I was drawing, is a very generic formulation of at least 1 + 1 dimensional quantum systems. So I think there remains many things to be done. For example, you could pick other minimum models and couple them together and look at what's happening in the infrared. So it's not so hard to do that because of this anyon formulation. And there's one thing I'm doing now with Antonio is to look at the interface between tricritical easing model and POTS model. So I mentioned that if you favor the fusion channel to be 1 particle, you get tricritical easing. If you favor it to be the W particle, you get actually the POTS model. So you can build the interface between them. And this is actually related to what Marco talked about in first week. If you fold this theory, you get a theory with central charge equal to 1.5. So maybe we can find new interface. Maybe even try to build a topological interface and merge it to get something for SU2 level 2. That's something to do. And of course, this is the Bootstrap conference. With Francisco, Madalena, and Bout, we are trying to do modular bootstrap of this big symmetry. I think that's a very interesting direction. Also, we are not doing it, but maybe 4-point functions decorated by these webs are interesting. That's it. Thank you very much.